Now we will talk about transistors. Transistors is not a new concept, especially when you know about p-n junction, because the concept of transistors is merely the extension of the concept of p-n junction. So as usual, first we will review some of the previous concepts and then we will talk about transistors. And I gave very long and detailed lectures about p-n junctions and about the semiconductors and many other things. So those lectures are prerequisite for this lecture, because if you don't understand the preliminary or the basic concepts very clearly, you will not be able to understand the concept of transistor, because it is the extension and it is a more complicated case of p-n junction. So if you haven't watched my previous lectures, please watch them first, understand them very clearly, and then come back to this lecture, because although I will review some of the previous concepts, but I will go very quickly. They are not enough if you haven't watched my previous lectures, because I give the introductory treatment of the subject is just to refresh the knowledge you have learned from my previous lectures, and it will just refresh that knowledge so that you will understand the forthcoming concepts. So the story began from intrinsic silicon. Silicon is a semiconductor, and you know that a semiconductor is usually behaves as an insulator at normal temperature, and but we can change its conductivity according to our desire. And how can we change its conductivity? Here I have intrinsic silicon. Intrinsic silicon means pure silicon, this material, a block which is made of pure silicon atom. You see that all of these are silicon atom. Silicon has 4 valence electron, and this is the way I show atoms. I only show the valence shell and the electrons in the valence shell, and rest of the structure of the atom is hidden. Then we learned that we can change the conductivity of silicon by doping. And what is doping? Doping is that I can replace some silicon atoms with another material, and it depends. For example, if I have a material which is trivalent, trivalent is a material which has 3 valence electrons in the valence shell. An example of trivalent is boron. Boron has 5 electrons and 5 protons, and distribution of these 5 electrons is like that. In the first orbit there are 2 electrons, and then in the outermost shell or valence shell I have 3 electrons. So you see, and this is my way to show the atom in a short form so that I have enough space to show everything, because I don't want to show a complete picture of the atom every time, and because we don't care about the electrons in the first shell or the completely filled inner shells. So that's why I show only the outermost shell and the electrons in that one. So boron. So a boron is a trivalent atom because it has 3 electrons in the valence shell. But boron is not the only material which is trivalent. There are some other materials as well. Similarly, second case is that I can replace one or more silicon atoms with pentavalent atom, because I have the choice. So the example of a pentavalent atom is phosphorus. Phosphorus has 15 electrons, 15 protons. So if you see the distributions of the electrons around the shells, 2 electrons are in the first shell, then I have 8 electrons in the second shell, because we have a rule which says that the distribution of electrons around the shells follows a rule like this, where n is the shell number. So the first shell which is nearest to the nucleus is the first shell. So if n is 1, so first shell can have only 2 electrons. Then in the second shell it should be 8 electrons, and then in the third there should be 18 electrons, but unfortunately we are left only with 5 electrons. So there are 5 electrons in the third shell of phosphorus. That's why phosphorus is a pentavalent atom. And I will show pentavalent atom or phosphorus atom like this. I will hide all the detail of the inner completely filled inner shell, so that we only see the valence shell and number of electrons in that. So now I have the choice that I can either replace silicon atoms with a trivalent atom or pentavalent atom. So let's do that. So as an example, for example, I take out this silicon atom and I replace this silicon atom with a trivalent atom. So here is a trivalent atom. A trivalent atom has 3 electrons in the valence shell. Now what will happen? So I will go very quickly that in the semiconductors the bonding is covalent bond. So this trivalent atom will make a covalent bond with the neighboring silicon atoms, for example this and then this, and this may make a covalent bond with this one. But now this electron of the silicon atom is left, because when there is a silicon atom, all the silicon atoms have 4 valence electrons and they can make 4 covalent bonds with the neighboring atoms. But now I have replaced silicon with a trivalent atom, so now the electron of one neighboring silicon atom is unable to make a covalent bond with. So in this situation we say that a hole will be created. For example, here hole is just a vacancy for an electron, that this material wants an electron so that an electron can come here and it can make a covalent bond with the neighboring silicon atom. And we call this material, when we replace a silicon atom with a trivalent atom, so now here there is a vacancy for an electron. So we call this material as p-type material. And because of this change, the conductivity of the material will change. Similarly, if I replace a silicon atom with a pentavalent atom, because a pentavalent atom has 5 electrons in the outermost shell, so we can according to the rule, the 4 electrons will make a covalent bond with 4 neighboring atoms. So this may make a covalent bond with this atom, this may make a covalent bond with this one, and this one can make a covalent bond with the 4th neighboring silicon atoms. But now what will happen to the 5th electron of the pentavalent atom, because it has 5 valence electrons? So this one is left, so it cannot make a covalent bond with any neighboring atom, because there is no neighboring atom for this electron to offer an electron for covalent bonding. So in this way this electron will gain some extra electrons which are not in covalent bonding. And of course we know that the valence electrons are loosely bound with their nuclei, so if we apply even a little electric field, they will start flowing through the material, and this is the way conductivity of this material will change. So we call these type of material n-type semiconductors or n-type silicon. So we have already studied them. So here I want to add one more information, that most of the atoms are electrically neutral. For example, if you see that a trivalent atom, for example boron, it has 6 neutrons, and it has 5, and neutrons are electrically neutral, so we don't have to worry about them. It has 5 protons, protons have positive charge, and then it has 5 electrons around the nucleus. So it is electrically neutral. 5 protons, 5 electrons, and charge of protons and electrons is equal but opposite. So it is electrically neutral. Of course, silicon is also electrically neutral. So this whole material, p-type material, no matter how many holes it has, it is electrically neutral. So some students might think that I am calling it like p-type material, maybe positive material, or it gains some type of positive charge. No, it is electrically neutral overall, because all the atoms in the material, no matter how many silicon atom I replace with a trivalent, because every trivalent atom is also electrically neutral. So it is not adding or deleting some type of charge from this material. There is no change in the electrical charge of this material, so it is neutral. But just because of a convention that it is wanting an electron in this place so that it can make a covalent bond with the leftover fourth silicon atom, so that in that sense we call it like a p-type material, because it is in want of electrons so that it can make a bond with. But overall the charge is neutral. I mean, the number of protons and number of electrons in this whole material, they are equal. And same is the case for n-type. But because we say that we have some extra electron, but it is not an extra electron. It is extra electron in the sense that it is unable to make a covalent bond with a neighboring silicon atom. But it is attached with its nucleus. And this pentavalent atom, for example, a pentavalent atom like phosphorus, we see that the number of protons are 15, number of electrons are 15. It is electrically neutral. So in the n-type, no matter how many a type of free electrons you get, it doesn't mean it gains some type of negative charge. No, it is electrically neutral, but we call it n-type because it has some loosely bound electrons that when we apply a type of electric field, this material will allow the flow of electrons, and flow of electron means current will start flowing. It means conductivity will change. So we call them p and n type in that sense, but it doesn't mean it gains some type of negative charge. No, it is still electrically neutral. So far I have been talking generally about doping. I replaced one silicon atom with one trivalent atom. Similarly here I replaced one silicon atom with one pentavalent atom. So if we want to quantify the doping level, for example, if I ask you what is the doping level in this case, you can say that I replaced one silicon atom per 8 silicon atoms. There were total 9 silicon atoms in this case. Of course, this is an exaggerated picture of silicon material because there are billions and billions of atoms in one piece of material. And but because this is an exaggerated picture, so I can't show you like billions of atoms in this material, otherwise you won't be able to see every atom and then valence electrons, because I wanted to show you how they make covalent bonds with the 4 or 3 neighboring silicon atoms. So when I replaced one silicon atom, there were total 9 silicon atoms and I replaced one out of them. So you can say like there were total 9 atoms and you replaced one silicon atom. So as a rough estimate, you can say that you replaced one silicon atom per 8 silicon atoms. So it means if I follow this rule, I will replace another silicon atom after another 8 silicon atoms. If I go to if I go in any dimension, then after another 8 silicon atoms, I will replace one silicon atom with trivalent. Then after passing another 8 silicon atoms, I will replace one more silicon atom with a trivalent atom. So this is the way we can quantify the doping level, right? Because we can calculate what is the doping level. So there are two conventions we use. Sometimes we say that is it heavily doped or lightly, or the doping level is low. So how can we say that? So let's talk about the real situation. So usually if I add dopant atom, one dopant atom per 100 million silicon atoms, this doping is called low doping or light doping. You see, the real numbers are really large. If I add one dopant atom, whatever it is, it may be pentavalent in case of n-type or trivalent in case of p-type. So if I add one dopant atom per 100 million silicon atoms in that material, it means I will replace one silicon atom with one dopant atom after passing 100 million silicon atoms. Then I will pass another 100 million atoms, and after that I will replace one silicon atom with one dopant atom. Then I will pass another 100 million silicon atoms. The same is the case in the way we had in this example. Then this type of doping, we usually refer it as it is light doping. You see, because I leave a large number of silicon atoms and I replace then one silicon atom with one dopant atom. Then I cross another 100 million silicon atoms. So this doping is really low. You can imagine from this number, because I didn't write it in scientific notation, so that you can imagine that I am leaving a huge number of silicon atoms, and then I replace only one silicon atom after that with the dopant atom. So such type of doping is called low or light doping. Okay, so then what is heavily doped material? When do we say that it is heavily doped? The general rule says that if I add one dopant atom per, what you think will be this number per silicon atoms. So what you think that number will be around? That is, the number is around 10,000 silicon atoms. So if I add one dopant atom per 10,000 silicon atoms, it means I will pass by 10,000 silicon atoms, and then I will replace, when whatever is the atom after the 10,000, I will replace it with the dopant atom. Then I will pass through 10,000 silicon atoms, and I will replace the next silicon atom with the dopant. And then this will go on. So this is called heavily doped material, and this is heavy doping. So just forget about my numbers and my exaggerated pictures that if I replace one per 8 silicon atom, this is just nonsense. So a heavily doped material this is just the estimated value, so don't take it very serious like this is the exact number. That if I add one dopant atom per 10,000 silicon atoms, or around 10,000 silicon atoms, that is called heavily doped material. And I want to add one more thing, that if a material, for example, this is p-type material, right? And if it is heavily doped, then we usually use a symbol, we add a plus sign. And if it is n-type material, then we can add a positive sign with n. So if you see, if you are reading literature and then you are reading about p-type and n-type materials, and if they write it p positive, it means it is heavily doped. What does it mean? That there is one dopant atom per 10,000 silicon or whatever semiconductor is used, and this value is of course is estimated. The value should be around 10,000. And similarly, in case of light doping, as I told you, that light doping means I will add one dopant atom per 100 million silicon atoms. And this doping is called light doping. And if a material is lightly doped, then we usually add a negative sign with N. So don't confuse it with N ions or something like that. If you are reading a literature about semiconductors and specifically about doping or something, and if you see a negative sign with P and N, it means it is lightly doped. What does that mean? That there is one dopant atom per 100 million silicon or whatever material is used, and once again this value is a rough value, so there may be some deviation. Then we learned that if we combine N-type and P-type materials at a molecular levels, then the the charges, they they diffuse across the boundary where the two materials are combined, and then an electric field is developed across the junction. Negative charges are accumulated at the edge of p-type, and then as a result of that, a type of positive charges are developed across the edge of n-type. An electric field is set up, and this electric field stops the diffusion of further electrons. If they want to go to this side, they can't, because now an electric field is set up. This is how the diffusion works. And this is the way it is different, because when I was a student and I used to think like that, so I was always curious. So once I asked my teacher that, for example, if I have two chambers in which one I have hot water and in the second chamber I have cold water, or you can say just normal water, and I say if I remove this barrier, so what happens? The hot and cold water, they diffuse with each other and they mix up, everything recombines, all the molecules, they just recombines, and we get a total water with the temperature is the difference of cold and hot water. When whatever is the temperature, it will become, it will reach at equilibrium. So everything is just mixed up. And that's why I was surprised. And then my teacher told me that that is a different case. You are talking about hot and cold water, and they are liquids, and then they mix up. Here we are talking about charges, positive and negative charges, and this is the behavior when they diffuse across this junction, and in special circumstances when they are combined at molecular scale, and we let them diffuse across this junction where the point where the two materials are joining. So this is the way it happens with the charge. Charge distribution is different, and you can't compare it with a situation like hot and cold water. And then we have an electric field, and then we also learned that we can use this PN junction in two ways. In one way, we can attach positive, and here is the negative side of the battery. If we attach positive side of the battery with p-type and n-type side of the PN junction with the negative side of the battery, it is in forward bias mode. The current will flow from negative to the, as long as I cross this barrier, the voltage of the battery should be greater than this voltage, which is around 0.6 volt. In case of silicon, voltage of the battery is 1.5 volts, so we will see a flow of current. And if I reverse the terminals of the battery, no current will flow. That's why I said that a PN junction allows the current to flow only in one direction and not in the other way. That was the unique feature of PN junction. And then we saw that because of this feature, we saw that we can rectify alternating voltage into a type of DC or pulsating DC voltage. And of course, after we have studied P and N type material, and just imagine if you are studying this type of thing, what can you think you can play with this type of device? Can you say, like, can you make something else? Or do you have any questions? Like, you are combining P and N type and you made a device. So just imagine if you are working in the laboratory and you want to do some new experiment. You are just bored with this stuff. You have P type, you have N type, you have already explored the forward biasing, reverse biasing, you have seen some applications. What else can you think to make something new out of it? Or are you curious about? So it's very natural to think that I can make another device like this. Because of course, if I am curious, I know that there is a N-type and then the P-type, and it is a PN junction. But what if I have N-type, P-type, and then I make another junction on the other side with N-type? What will happen? It's like two diodes in reverse directions, right? Yes, so that was the case at that time when the PN junction was there, and some scientists, they were just curious, and then they were just curious to see what will happen if they make a setup like this. They have two Npn junctions side by side, and of course it is at the molecular scale once again, like the diffusion. And then they did some other experiments. They changed the area of one region and they increase the area of the other region. They did a lot of experiments, and even they changed the doping levels of the different regions just to see like maybe they can find something interesting out of this device. It is just the extension of p-n junction, right? Because we already studied like a p-n junction is p and n type and they combine at molecular scale. Now we have another p-n junction on this side, and that time scientists discovered a very, very interesting feature of this device. After some experimentation, of course, this is a raw figure, and they changed the areas of different regions, they changed the doping levels, and then they found an interesting device of something like this, and that was actually transistor. And now we will talk about the properties of a transistor and why it is a magical device, and it is more interesting than just p-n junction. I show you a more realistic structure of transistor. So here I have a basic and of course exaggerated structure of a transistor. So you know that a transistor is actually a combination of two diodes. One is directed to the left in this case and other directed to the right side. That's why we have two junctions. And on the left side I have N-type, then I have sandwiched P-type semiconductor in the middle, and then I have put another N-type on the right side. So that's why we call this type of transistor as NPN transistor, because P-type semiconductor is sandwiched between two N-type semiconductors. And of course you can suggest that why not we make a transistor where the p-type semiconductor is on the left, N is sandwiched between two p-type semiconductor materials. And of course we also have transistors with this structure, but NPN is most common. So let's talk about NPN transistor, and basic operation and everything is similar except the direction of the current. So we will not talk about PNP. Let's try to understand NPN and just stick to one convention, so that we understand the basic operation structure and what is going on inside. And later on, it is easy to shift to the PNP if you want to. Similarly, in all of this discussion, I will take real current. It means I will take direction of current from negative to positive terminals wherever it is possible, or from lower to higher potential. For example, here I have ground and then I have a positive. So if I am connected with ground and negative, current will flow from negative terminal to the ground, because ground will act like a positive terminal because it is at higher potential than negative terminal. Similarly, if I am connected with the positive and ground terminal, now ground is at lower potential and positive is at higher, and lower potential is always, we can treat it like negative. So now here ground is negative, so current will flow from ground to the positive terminal, and I will remind you with this during the discussion. So how did they make a transistor? And this is a bit realistic picture of a transistor, and let me tell you what are the changes they made to get the desired output or desired operation. That's why it revolutionized digital electronics. So they made p-type, which is sandwich in this case because we are only talking about npn, so I will only say p-type, but when you are talking about pnp you can easily replace it with n-type. So let's forget about pnp and stick with npn. um, so here we have p-type in the middle, and this region is very small in relevant to the n-type on the two sides. So this one is very small and it is lightly doped. So most of these things will be cleared when I will talk about the applications of transistors. For example, when we will use it as an amplifier, or I will discuss different cases of the transistor, then I will clarify why the and they call this central part as base. So we can give it a name, then it will be easier to talk. So these are the real name they gave. The central part, which is in this case is p-type, which is sandwiched between two n-type semiconductor, it is called base. Similarly, the left one, which is larger in area than the base, and it is n-type, we call it emitter, and it is heavily doped. So as you can see that you can only see the pentavalent atoms and you can't see any silicon atoms. It is representing that it is heavily doped with pentavalent atoms. You know that pentavalent atom has 5 electrons in the valence shell, 4 are bonded with the neighboring silicon atoms if they are present, and 1 electron is left, which conducts through the material if we apply an electric field or if we apply a potential difference across the two terminals, and it depends which terminal. If it is in forward bias, then they will conduct, otherwise they won't. So this one is heavily doped and they call it emitter because during the operation they want to use it to start the current. So if you can consider it like a reservoir, it's a reservoir of charges. So when they want to operate it, they want to use it as a reservoir of free electrons or loosely bound electrons, so that it will emit electrons out of this region, and so that they can conduct current if the situations are favorable. For example, if it is in forward bias, for example, because there is a junction, this is a junction, and we know that if the situation is favorable mean if it is forward bias, then of course it will emit electrons. I mean, it is ready to give electrons if the situation is right. And then we have a lightly doped, more lightly than even the base, and they call it collector because during the operation they use it to collect electrons which comes from the n-type side, which is on the left side. So this is n-type, which is emitter. Here we have collector. So the collector will behave like to collect electrons which are coming from the emitter and base. So it will collect electrons. So if it wants to collect electrons, we don't want free electrons in this region, right? Because the basic function of the collector is to collect electrons which are coming from the left, from the n-type, and of course they will pass through the base and then they will come to this side. So if it wants to collect electrons, then we don't need many electrons. So you see, I have only one pentavalent atom here. It is just showing that it is extremely lightly doped. Only one pentavalent. Rest are just silicon atoms because we don't want free electrons in this region. We will get those free electrons from the emitter, which is a reservoir of free electrons. So I am showing only one pentavalent here. It is showing that it is lightly. In fact, the doping level, suppose the doping level for the base is D, then the doping level of collector will be 1 over 10th of D. So the doping level of the collector is 10 times lesser than the doping of the base. because I have already told you that base is lightly doped, but collector is even more lightly doped than the base. So the collector is 10 times lighter than the base doping. This is the way it works. Now how about the base? The central part, which is sandwiched between two opposite type semiconductors, is called base, and as I told you, it is very thin and it is lightly doped. So that's why you can see like there are two trivalent atoms. I mean, trivalent atoms are the atoms which have 3 valence electrons, and then I am showing only one silicon atom, so it is showing like it is lightly doped. But if I show like there are so many silicon atoms and only one pentavalent, it is showing it is even more lightly doped than the base, because for two dopant atom I have only one silicon, but here I have so many silicon atoms, 7 silicon atoms with one dopant, so it is even lighter than the base doping. And you can't see any silicon atom in the emitter, so it is showing like it is heavily doped. And now you know the conventions. So I can operate this device, which I am calling as transistor, in many ways, right? Because now I can either make this and this junction forward bias, and then maybe this and this as reverse bias. There could be many possibilities, right? Or I can make this one reverse bias and the next junction as forward bias, or in the third case I can make both reverse biased, right? So I can either make both junctions forward biased, I can make both junctions reverse bias, or I can make one forward bias and one in reverse bias. So there are many possibilities, and I will explore how can we do that. So here I have an Npn transistor and all the labels are there. So how can I connect its terminals? Because it has 3 terminals and now there are 2 junctions in that. So let's first talk very basic configuration. I have a battery here. Here is the positive terminal and here is the negative terminal. So if I connect positive terminal with the n-type side on the right, and if I connect negative terminal with the n-type on the left, which is emitter and collector, so I know next on I will call it collector and emitter, because although these both of these sides are n-type, but they are not identical. First, they are not identical because the left side n-type, which is emitter, A has less area than the collector. Collector has large area, and I will tell you later on when I will talk that why it has large area. And base is very thin, and why n-type is in the middle. It has area but not equal or greater than collector. It is in the middle. And then doping, it is heavily doped, but collector is lightly doped. So that's why I will call them collector and emitter, not as n-type, because there are 2 n-types. So in this configuration, what do you think will happen? As you see that n-type side is connected with the positive terminal of the battery, and emitter is connected with negative terminal, and collector, which is also n-type, is positive. So in this way, one junction is in forward bias and one junction is in reverse bias. So can you tell me how? Which one is in reverse bias? See, here it is n-type, and if n-type is connected with positive, it is in reverse bias. So just this junction is in reverse bias mode. But this n-type emitter, the emitter n-type is connected with negative terminal. So it means this junction is in forward bias mode, because of course the p-type, this p-type will act like it is connected with positive terminal for this junction, because here is the symbol of the diode. So if we consider this junction, we can say like this p-type is connected with positive terminal, because here is the positive terminal, although this positive terminal is connected with the n-type, but this n-type is connected with the p-type. So we can assume like this p-type is connected with positive, and here the next side is connected with negative terminal. I mean n-type is connected with negative and p-type is with positive terminals. So in this situation it is in forward biasing. When we want to consider this junction, just see the image. Now this n-type, collector n-type, is connected with positive terminal, and now here we can see that this p-type is connected with this side, although this negative is connected with the emitter n-type, but this is connected with the p-type as well. And if you see the symbol of the PN junction diode, we can say like this is connected with negative and this one is connected with positive. So this junction is in reverse bias mode. So one junction is in forward bias, so current will easily try to flow into this direction. But then this junction is in reverse bias mode, so it will not allow the current to flow. So what will happen? No current will flow, and we can say that this transistor is in off mode. It is off because no current is flowing. So it is off, although one junction is in forward bias mode, but it's useless because the next junction is in reverse bias mode and it will not allow the flow of current. Now this is off. Now I have one more question. What if I reverse the sides of the battery? Or I can say if I change the terminals of the transistor, will it change anything, or will it remain off? Because no matter how I change the terminals of the battery, even if I reverse the sides of the terminal, one junction will always be in reverse bias mode and one junction will be in forward bias mode. Of course, in that case it will change. Now this junction will become in reverse bias mode and this will become forward bias. But situation is same, right? Because if there is one junction in reverse bias mode, it will not allow the flow of electrons across it, and no current will flow eventually, and it is still off. But one thing I want to clarify, that it is not identical. That if you connect collector n-type with one terminal and emitter n-type with other terminal, the situation, and then you reverse the terminals, this situation is not the same. Don't think it that simple, that this okay, here is n-type, here is n-type, so it doesn't matter if I exchange the terminals of the battery in this situation. No, it's different. Although the eventual result in this case is same, it is still off. But always remember that this n-type, which is collector, and this n-type, which is emitter, they are different. Now these junctions are different, you see. Their areas are different, and these different areas will matter later when I will explain their operation in more detail. And then the doping level is different. So these two terminals are different. They are not only n-type. That's why I will call them as emitter n-type and collector n-type, or just collector and emitter, because n-type will help us to understand what is the terminal and what are the atoms. So remember that merely exchanging the terminals of a transistor is not identical and it is not advisable. You must be careful when you are connecting a transistor in your circuit, that where is the emitter and where is the collector. So this setup is very basic, and we are actually not using it like a transistor, because you know now we have three regions, N, P and N, and but we are only connecting two regions with the battery terminals, and the middle part, the P type or the base is not connected with any voltage source or power source. So we are not using it in a proper way. So in the next we will see how can we do that. Before I go forward, let's see how will I show the power supply. I showed you that this is a common DC power supply. It can give negative 20 volts at most or up to plus 20 volts, and this is the ground, or we call it a common port. So if I use this power supply in the laboratory, then it means I can connect one end, suppose, of the component with negative 20, and then there is plus 20, So the total potential difference is 40 volts if each is volts. And this is the common port which is usually in between, and it represents that there is no potential, it is 0 volts. So next I will take this part of the power supply to show that how will I connect the different terminals of the transistor. So I will show this image as positive, negative and ground floor, because of course I will represent different potential levels, for example maybe -5 and +2. So that's why I will show this image, so that when I want to apply a certain voltage I can write it along with the line. And of course all of the analysis will be on DC voltage or DC current, mean whatever I apply the voltage it will remain the same at least during that analysis, and then of course I can change it to the next level and then take another measurement, then change, that is, but by nature this voltage is not changing as long as I am connecting. And I can change this voltage using the knob given here. So if I rotate I can give maybe -1 or +1. If I rotate it further it can go up to -2, +2, so on. And I can use different power supplies, of course this is not only the one, so I can use two of them. So here let's see the analysis. So here I have the power supplies. So just imagine I have two type of those power supplies, and I can set the potential at different levels for each. And now I want to do this analysis. What I am gonna do, I want to connect, here I have the power supply, so I take connection negative potential to p type. So I connect p type side of this transistor with the negative terminal, and let's say that the potential is at -2. The next is ground. I connect ground with the emitter n type. So you see now I am connecting the base with a certain potential. The next I connect collector with a positive terminal of this power supply here. And I set this potential at +5, let's say, +5 volts. Of course, all the values are in volts. And this ground is of course 0. And then I connect this emitter with the ground. So you can say that this ground and this ground is actually same ground. And in this setup we call it that this is common emitter mode. So this setup which I am presenting now, it is common emitter because emitter is common to both base and collectors. You see that hey, this is the emitter, this is connected with the base through this power supply. Similarly this is also connected with the collectors this way, so it is common. So just imagine that these ground terminals are same, it is not two separate terminals. This is same because both of them are at 0 volts. So even I can use same power supply for this terminal. So this is connected to one terminal because one is connected with the positive. Now let's see what will happen. What do you think is the mode of operation of this PN junction, mean the emitter base junction? What is the mode of operation of emitter base junction? Is it forward biased or reverse biased? So let's see. The p type base, which is p type, is connected with negative, so I always show -2 at lower level, and the next is at ground. So ground is at higher, and then I represent positive voltages, V positive. So it means current will always flow from -2 to the ground. So it means ground is positive and this is of course negative because current is flowing from -2 to ground. And if negative 2 is at lower potential, then ground is at higher potential. It means it is more positive than negative 2. Although it has actually no, it is 0 volts, but you can say in this reference, because negative 2 is lower than that, so it is like more positive than negative 2, so G is positive. It means G is working as a positive, so it means this n-type side is connected with positive terminal. And this is of course negative. So p-type side is connected with negative terminal, and n-type side of, if we consider it like p-n junction only, not a part of transistor, then of course this is a p-n junction, and that the p-type side of the p-n junction is connected with negative and n-type side is connected with positive. This is in reverse bias mode, so no current will flow. So let's see for the next junction, the base collector junction. Here, what is the mode of operation? So you see that this is also a p type, p n junction, so let's treat it like that. Here is the p type. P type is negative, right? It's negative 2. So I can represent this as negative 2. Then ground is in the middle, and then the n type side is at plus 5 volts. So now how do you think they are? Of course, this is at higher potential, current will flow from negative to plus 5. So this is negative terminal, this is positive terminal. And now let's see what is that. N-type side is connected, if we consider this one as a p-n junction, that N-type side is connected with positive potential. And p-type is with negative. So this is also in reverse bias mode. Both junctions, emitter base or base collector, are in reverse bias mode and no current will flow, absolutely no current. Just forget about minority charge carriers or something like that. So no current will flow. In this mode we call it that this transistor is in off mode. It is off. And we call this mode of operation as common emitter because emitter is common to both collector and base. Let's do another experiment. This time I will connect this base with the positive terminal of this power supply, okay, here. And I connect and I set this voltage at plus 5 volts. The emitter is once again connected with the ground. For the collector, I connect it with a positive terminal here of the power supply. And I set this voltage at plus 2. And of course, emitter is common because this is common emitter mode. So emitter is common. So I will connect it with the ground. It is common to both base and collector. It is connected with both. Now let's see what is the mode of operation of base emitter junction, and then we will see what is the mode of operation of base and collector junction. So let's first see what is the mode of operation of emitter and base junction, this one. I think this one is easy because the p-type base is at plus 5 volt. So plus 5 volt. Then we have ground somewhere in the middle at 0 volts. And then we have some negative, which we don't have any. But if there is any, negative is usually below ground. So now the p-type base is connected with plus p or plus 5p, and n-type emitter is connected with ground, and in this case current will flow from ground to plus V. It means ground will serve as negative. Ground is will serve as negative because in reference to plus 5 volts. if we can consider it as a p-n junction, then of course p-type side is connected with positive terminal of the battery and n-type side is connected with the negative terminal of the battery. This G, as I told you, that is serving as negative terminal in this case, because the next point is as plus 5V. So in reference to plus 5, G is lower in potential in my convention, and it will serve as negative terminal. So this is one now is in forward bias mode. This junction is in forward bias mode. Let's see if the base collector junction. Here is the base collector junction. So the n-type collector is at plus 2. So if I want to use this map, or let me make another. So if here I have plus 5 volts, then of course plus 2 volt is lower than that, plus 2 volt. Then we have ground, and then we have negative voltage if there is any. So now n-type is connected with plus 2, here is plus 2, and the other side, which is p-type base, is connected with plus 5 volts. And you see the lower plus 2 volt is lower in potential than plus 5 volts. And in reference to in this convention, plus 5 volts is more positive than plus 2 volt, right? Because it is at higher value and higher potential. So we can think like plus 2 is negative terminal, because plus 5V is more positive than plus 2V. So it is more positive, then this will is like is serving like a negative terminal, because current will flow, if it is allowed to flow, from plus 2 to plus 5 volts. It is lower potential and lower value, we take it as negative. It doesn't need to be below ground like with negative symbol. If a potential point is at lower and one is at higher, so higher is always positive and lower is, we can take it like negative. So it means this one is negative. So n-type side is connected with negative terminal of the battery, and p-type side of this p-n junction, which is now part of a transistor, is connected with positive terminal. This is also in forward bias mode. So what will happen now? What do you think will happen? Both junctions are in forward bias mode, so a huge current will flow through it without much resistance. And in this mode of operation, we call it that now the transistor is on, or it is in saturation mode. Saturation means a lot of current will flow and there is basically nothing we can do. It is like a conductor. Like we have connected two terminals and through a wire, and current is just flowing freely. So we call it saturation mode, or the operation or mode of operation is in saturation mode. And this is not very desirable, but in this case it will work as on. Like now the transistor is totally on. The first case in which the both junctions were in reverse bias, it was off. Now this is in saturation mode. The current will flow throughout this device, and there is nothing special in this mode of operation, right? Next, I want to set this voltage at plus 5 volts, and I will set the base voltage at plus 2 volts, and then we will see what happens, because it will change something. So here I have a new setup, and let me set up the connections. So I will connect the base, which is p-type, with positive terminal of this power supply, but this time I will set the voltage at plus 2 volts. These are just values we want to, and then of course I will connect n-type with the ground, and now I will connect collector, of course, with the positive terminal of this power supply, and this time I will set this voltage at plus 5 volts. And then I will connect emitter with ground of this power supply, so that emitter is common to the base and collector. Now let's see what will happen. First we can check the emitter base junction here, and let's see what is the mode of operation. So Let's see, it is at plus 2 volt potential. The base is at plus 2. Then we have ground, which is in the middle, lower than plus 2. Current will always flow from ground to the plus 2 terminal. Plus 2V is more positive than ground, so ground will work like negative terminal. N-type side of this PN junction is connected with the negative terminal, and P-type side of this junction is connected with the positive, and this is in forward bias mode according to the definition we know of the PN junction, which is now part of a transistor. So this junction is in forward bias mode. Now come to the second junction, which is base collector junction, and let's see what happens with this junction. The n-type or collector n-type side of this junction is at plus 5 volts, and then p-type side or base is at plus 2 volts potential, and then we will have a ground, and then after ground we will have negative voltages. You see, so the n-type side of this PN junction, if I just take it as an individual PN junction, then n-type side is connected with positive side, and p-type side is connected with negative terminal, because you know now plus 2 is at lower potential than plus 5 volt potential. It is higher potential, it is more positive than plus 2 volt. So plus 2 is like in negative terminal. So this p-type side, it seems like for the first one, this one is very interesting to see, like this the same p-type, and with it is connected with the same terminal. But when you consider its operation with reference to the emitter or n-type side, it serves as positive terminal. But when you consider its operation with reference to the n-type side, which is connected with plus 5 volt, it's the same terminal is now as a negative terminal. You see, this is because of the potential difference, because when it is still at plus 2, but when we see that the reference point is ground, then ground is negative and this one is plus, because this is now more positive with reference to the ground. But when we are taking plus 5V and plus 2V, now plus 5V is more positive than plus 2V, so this is negative. The same connection, same reference, but just because reference of the other point is different, the behavior of this point is different. Now this one is second, it is negative terminal. So we see that p-type side is connected with negative terminal of the battery, and n-type side, which is collector, is connected with positive terminal. This is in reverse bias mode. One junction is in forward bias mode, mean the emitter based junction, and the collector based junction or base collector junction is in reverse bias. And in this mode, we call it that this is active mode of the transistor. This is active mode, and when we draw the output characteristics, we want to see its characteristics in the active mode, because this is the real operation of the transistor. We want the emitter based junction always in forward bias mode, and we want base collector junction in reverse bias mode. This is the active mode operation or the correct operation of the transistor. So never think like we want to make emitter base junction reverse and base collector junction as forward. Never think like that, because we don't want to use it in that way. And the reason is that we have reserved this region, which I am calling as emitter, and it is heavily doped. It means it has a lot of free electron. So it is like a reservoir of so many electrons, and we want to use this region as a reservoir of free electrons. So if we want, it will emit free electrons to the base. It will eject them to the base, right? So if it wants to eject to the base, we want this junction to be in forward bias mode, because that is the only way it will eject its free electron to the base. Of course, because if you have a collection of something, you want to take something out of that collection, right? You will not close the way out of those things, because this is like a storage, and when you need something, of course you will want to take that out of the storage, so you have to keep that way open. So we want to use this junction in forward bias mode, so that whenever you need, you take these electrons out into the base. And now let me show you like that what happens when this one is in forward bias mode. So just see, like we have a lot of pentavalent atoms, and you know that pentavalent atom, we have free electrons with them because there are 5 electrons in the valence shell, and this one electron is not very well connected with the nucleus, and it is not even engaged in covalent bonding with the other silicon atoms, because there are 4 electrons. They make covalent bonds with 4 neighboring silicon atoms, but 1 electron is left, so it has a lot of free electrons. So in this case, suppose this electron will just go to the base, because we want to see what happens in this mode of operation. It's very interesting. When it comes to the base, then there is a probability that it will recombine. Recombination is a process that, because in the base we see that there are holes. Of course, it is lightly doped. There are some silicon atoms as well, but there are holes as well. So there are 2 probabilities. First probability is that this electron, it will fill this hole. You know that hole is a vacancy of electron. This atom wants an electron. So if it gets any chance, the electron will immediately go to fill that hole. Then it will move to this hole, and then this way a current will start flowing like this. Then another electron, of course, from another atom, then it will, of course, cross this junction, and you can see that in this case even the applied voltage is plus 2 volts, and we know that in case of silicon this potential difference across this barrier is about zero point 0.6 or zero point 0.7 volts. So this plus 2 volts is enough. So this electron will cross this junction because it has enough energy to oppose this junction, and it will cross, and then it will come, and then it will fill the hole, and then it will move another to the other hole, and then slowly it will go to the terminal, and then this is how the current will flow. But this is not one PN junction, and we already know this happens. When I gave the lecture about the PN junction, we saw this behavior, like this is how the current will flow, right? But now we have another junction, N type. So what do you think will happen to the other side, which is in reverse bias mode, this junction? So what do you think will happen on this side? And there is the magic. Because a lot of students say no current will flow. So they think like if we connect the terminals like this I have given, the current will just flow like this. So electrons will cross this junction, and of course they will move to this terminal, and this is how it will happen. But I tell you that there is very low probability that very few electrons will go to the holes, and then they will move to the battery, and this is a very small number of electrons will do that. And there is a big part of the picture which is yet to explore, and you know that what is that. So what do you think will happen on the right side? So a lot of students, they always guess that this current will keep flowing like that. So they say that this electron, of course this is not only one electron, there are many electrons. So many electrons will keep crossing the junction, of course, because this is in forward bias mode, and this is the way a current will set up. A current will flow like this. And when I say that what will happen to the right side, is there any chance that this electron may go to this way? They say no, how can it happen? Because this junction, mean the base and collector junction, it is in it is in reverse bias mode, right? Just we know that this n-type side of collector is connected to the positive terminal, and then this base is now acting as negative terminal, is connected to the p-type. So this is in reverse bias mode, so no current can go through the junction. Because so now I tell you the real story, that in fact a lot of electrons will cross this junction, right? So I tell you that only a fraction or very small amount of electrons will recombine. They will fill this hole, and they will flow. And large number of electrons, they will actually cross this barrier, and then they will go through this one. It means current out of the collector will be way larger than the current out of the base. For example, here, so if we have only one electron, and then Suppose if there are 3 electrons, they will make through this region, and only one will start recombining, will take part in the recombination here, 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 and only this one. So a small fraction of electron will actually go through this way, which you are thinking, and a large number of electron will happily cross this junction, and then they will go through this way. So again, so you will always get a large current from the collector and a small current from the base. And do you know the reason for that? Let me tell you the reason first, and then I will go into the further analysis. This base and collector junction is in reverse bias mode. I know that. But this reverse bias mode is only for the electrons which are present in the collector region. If there is any electron here, for this electron it's hard to cross the junction towards the left, of course, because now it is being snatched away from the positive terminal of the battery, of course, because this one is connected with positive terminal, and positive will attract it away from the junction. There is no force which can push it towards the junction, right? It was the different case when it was here. This terminal was connected with the negative side, so this negative will push it towards the junction. It's a different story. But if an electron is in the collector region, this is also an n-type, but unfortunately this n-type is connected with the positive side, so instead it will go away from the junction. There is no chance that this electron will go into the junction. So for the electrons which are in the n-type collector region, this is a reverse bias mode, and they will never, there is very low probability they can cross this junction. And as a matter of fact, there are very few free electrons in this region, in fact, because I told you this is more lightly, or it's very lightly doped. I told you that it is almost 10 times low in doping than the base. Base is also lightly doped. So there are almost no free electrons in this region. But for an electron in the p-type base region, this is forward bias. You know that now p-type is negative, right? P-type is negative when we are talking about the collector, because p-type is negative for the collector region. And if it is negative, this negative will push this electron, right? Because they are oppositely charged. So this negative charge will push this electron towards the n-type. So this reverse bias mode is only effective if there is any electron in the n region. But now we are getting electrons from the emitter on the left side, and the emitter is injecting electrons into the base. So we are getting electrons from the emitter. When they come here to these electrons, this junction on the right, the base collector junction, it is forward bias, because this p-type is like it is connected with negative terminal, right? And if it is negative, of course this negative will push this electron towards this, and in fact this applied voltage is plus 5 volts, which is larger than 0.6 or 7 volts in case of silicon. So a large number of electrons will cross this barrier to this one. And if you want me to remind, when I was explaining the reverse bias mode of p-n junction, if you remember from my previous lectures, I told you that in this reverse bias mode, you see the n-type side was connected with positive and p-type was connected with negative. And I told you that in this case, in fact, this barrier will become wide and wide, and no electron will be able to flow from the n-type on the right towards the p-type side on the left. Of course, because this is positive. So in fact, it will just snatch these free electrons away from the barrier, and it will bring them towards the right. They will go away and away from the barrier. But I told you that in case of some breakage of covalent bonds sometimes, or consider them like a manufacturing defect, there might be some free electrons available on the p-type side, and they are wandering around because of they are now broken. If there is a breakage of covalent bonds somehow, or just consider them as a manufacturing defect, and some free electrons are already present on the p-type, and I call them that they are minority charge carriers. To this electron, it's like a forward biasing, because now this is negative side and this negative will push this electron towards the other side. And I told you that still you will see some current even if it is in reverse bias mode and no electron can pass. Electron in the n-type region are unable to cross this. So I told you that there will be no current because of the majority charge carriers. Majority charge carriers are electrons in the n-type region, so they will not be able to cross to the left. And majority charge carrier in the p-type region are hole, and they will not be filled by the electrons in the n-type region. But if there are some electrons, due to the breakage of some covalent bonds, if the temperature is high, sometimes it happens, to this electron, it will fill this hole, this hole, this hole, or this hole. In this way, it will just go through the junction, because to this electron on the p type, it is actually forward bias mode. But of course, I told you that this number of these electrons are very small and it is not very significant in that case. But now situation is different. This emitter is full of electrons because it is heavily doped. So we have huge number of electrons emitter, and it is emitting the electrons continuously because this junction is in forward bias mode. And because of that, huge number of electrons are coming to the base, and when they come to the base, most of the electrons, they see this barrier as a forward bias mode. So they will pass through this junction and end up to the positive end of the terminal, because now you can see this, even this plus 5 volt is high. And the reason that a large number of electrons would love to cross this junction instead of recombination. I told you that if recombination occurs, if an electron, when it enters the base, it may go to the fill the hole. Once it fills the hole, then it will not be able to go through the junction. In fact, it will go to another hole, and then these electrons will constitute this current from the base. So we will see a current out of the base in this situation, and this current should be very small, and we will see a large current out of the collector. Every time when we see a little current from the basement, we will see a huge current from the collector. And the reason that only a small fraction of electron will take part in the recombination is the intelligent design. And that design is they make this base extremely thin. If it is extremely thin, electrons will not have enough time to recombine, and in fact, as soon as they enter the base, a large number of electrons will feel the push from this negative side, which is connected, towards the right side, and they will enter to the collector. Of course, in the collector it is very lightly doped, so they will go through the material. So only a fraction of electrons will recombine because of the small area, and a large number of electrons, when they enter the base, they will just go straight. And to these electrons in the p-type or base region, this is not reverse bias mode, it is forward bias mode. That reverse bias mode is only for the electron if they ever exist on the right side. So if an electron is here, to this electron, this is reverse bias mode, of course, because now the positive terminal of the battery is pulling it away from the junction. So there is no chance that it can ever cross the junction. In fact, it will just go away from the junction. But if an electron exists on if electrons exist on the p type or the base, to these electrons there is no problem, they will just cross, because to them it is like forward biasing. So this mode of operation, which is active mode, and this is how we use a transistor to amplify a current. You see, for a small base current, we get a huge current from the collector. If there is a small base current, we get a huge current from the collector, and this is called amplification. We can amplify a small current into a amplified current, and we will see the detail later. So now let's define some variables. So we have three currents, right? We get one current from the collector. So I give it a name I, which is the usual letter to represent current, and then I will write C in the subscript, which will show that this is collector current, which the current we get from the collector. We also get current from the emitter, which goes towards the base, and we call this current as IE, mean the current from the emitter. Similarly, we also get current from the base, and we just have seen that in common emitter in setup, for a small base current, which we can write it as IB, we get an amplified IC current. So you see that actually the emitter is the source of current. It is providing all the electrons. It has a storage of huge number of electrons, and because this junction is in forward bias, it sends so many electrons, and this is the source of current. So I can write an equation that IE equals IB plus IC. And it's very easy to understand, right? Because this current is divided into two sections. A small fraction uh, takes part in recombination, filling the hole, and that current flows out of the base towards the battery. But a large number of electrons, they want to cross the junction and go to this side, because the area of this base is small, and if area is small, electrons, a few number of electrons get a chance to recombine, and that current comes out of the base. And we see a huge amount of current from the collector, because they just go straight towards the collector. And that's why we can write that the emitter current is divided into two sections. A small fraction goes to the base, and it becomes a current from the base, and then we get rest of the current from the collector. So this is how we define the current. So remember these terms. And one more variables about the voltages. You see, so I have applied plus 2 volts across the base and emitter. So if I want to represent this, because here I use just specific numbers, but in the next analysis we will talk them in variables. So I will represent this voltage as V B E. That is right? Voltage across the junction, base and emitter. So that is the voltage across B and E, if I want to tell you about the voltage. Similarly, we also have a voltage across basement and the base and collector. So we will call that voltage as V, B and C. VBC mean the voltage across the base and collector, if I want to represent that voltage in terms of a variable. And we will see later that if there is a configuration in which we need to, because in this case this case is different, but we may see that there can be a voltage across collector and emitter. So we will call that voltage as voltage C and E, mean the voltage across collector and emitter in this, because this is also an important quantity we want to see. So if I want to represent these voltages and currents, we will use these variables. So as I said before, that common emitter setup or configuration is used when we need a high current gain. As you saw that a huge number of electrons will go through the collector, so we will see a huge current at IC for a small current from the base. That current is IB. So if we want to use this transistor as an amplifier, we will apply the input signal between the base and emitter. So that is our input signal, right? And that input voltage was 2 volts. and then we will get huge current. Whatever is the current for this IB, we get as a result of applying this plus 2 volts across base and emitter. We will get huge current across the collector and emitter. You see, we will get this current from these two terminals here and this. So here one terminal is coming from the emitter and the other is from the collector. So we give input signal at the base, because one terminal to the base, other to the emitter, and we get output signal from the collector and emitter from these two terminals, and we will get a huge current for a small base current. Now we want to see the characteristics of common emitter configuration of a transistor, which is also which can also work as an amplifier. So as in the case of diode, if you remember, we applied voltage, so that was our input characteristic, because we want to know what is the input, and then we want to see what is the corresponding output against that input. So if you remember, this is the reverse bias case of the PN junction, and then we applied some voltages across the PN junction, and then we saw that what is the corresponding output, and that corresponding output was current. And same was the case for forward bias. We applied voltages across the PN junction in forward bias mode, and then we try to understand that what is the behavior of the corresponding current. In the same way, now we will try to understand the characteristics of this transistor in a quantitative way. So as you know, we have three terminals in a transistor because of two junctions, and so we have three currents: one current from the collector, one IB current, base current, and then emitter current. And then we know that this emitter current divides into two sections. One is base current and collector, so the sum of these two currents should be equal to the emitter current, because emitter is actually emitting all the electrons towards the device. And now we will see that what is actually the input and what is the output. In this case, if you see that input is this VBE, we apply input signal across the base and emitter, right? These two connections, one is going to the base and other going to the emitter. So VBE is our input voltage, and if I want to talk in currents, IB is our input current, because this IB is the current against this applied voltage VBE, so IB. And then our output is IC, the corresponding current for this input current IB. And I told you that this IB is very small, and we will get a huge current at the collector in response to this small current at the base. And the corresponding voltage will be VCE, the voltage across the collector and emitter, because this is in common emitter mode. So emitter is shared between the basement, and on the other side it is shared with the collector. So we will get output at these two terminals, and we will give input at these two terminals, and you can see the relevant connections. So what are the input characteristics? The input characteristic is the voltage VBE and the corresponding current IB, because this is our input, for a fixed voltage across the collector and emitter. So we have a curve like this, in which here we have the voltage VBE, and then we record the corresponding current from the base IB, because now you are familiar with the names, and this is VBE. So you see, when the voltage across VBE is 0, we don't see any current from the base. So it is very understandable, if there is no voltage across, then of course no current will flow through this because there is a junction across the emitter and base. And if we don't apply any voltage across this junction, no current will flow, right? Next, we will increase the current, for example, to 0.2 volts. So just see that now the current across the junction base and emitter is zero point 0.2. So now if I connect this plus to the base, and now I will change this voltage slowly. And what should be the voltage across C and E? So of course I will connect it with the positive terminal. So initially we can keep this voltage at fixed point, for example at 10 volts. So this one is at 10, that one is ground, and this is connected with the emitter. Emitter is at ground and next is at plus 10 volts. So first we will fix VCE. This VCE is at 10 volts. Just fix any value and you can fix it. Then you don't need to change it. Or if you want to see the behavior, then you can take few measurement. First we will fix VCE at 10 volts, suppose in this case. And now I will apply this VBE because this is a variable power supply, so I can change it. So first I will fix it at 0. So when there is 0 volts, I don't see any current IB which is coming from the base, this IB. I don't see any current coming from the base because now we are considering only the input, so just forget about ICE. We are not looking at that. We are only interested in the input characteristics. Then we will see the output characteristics. Okay, because this is variable power supply, so now I can change the value to 0.3 or zero point 0.4. So every time I change the voltage, I will measure this current with an ammeter. So whatever, so it is showing me that current is 0. So I can see that yes, when it is 0.2, 0.3, 0.4, I don't see any current from the base. When I change the voltage to 0.5, 0.6, and as soon as I cross 0.6, now just see that VC is fixed at 10 volts for this experiment. As soon as I cross 0.6 volts B and E voltage, just see that when I increase this voltage, suppose to 0.7 volts, now I will start seeing some current out of the base. And you know the reason, right? Because if it is silicon and this junction is in forward bias mode, even if it is in forward bias mode, there is a potential barrier because of this recombination of the charges when they diffuse across each other, and there the voltage of this potential barrier is about zero point 0.6 volts in case of silicon. So when of course I have to overcome this barrier, otherwise no electron can flow towards the base. And you see, when I cross the zero point 0.6 volt across the base and emitter, I start seeing some current. And now, even with very little increase in the voltage, I see a big change in the current from the base. Although relatively this current is very small, and you will see later, because when we will see the current from the collector here, because now we are not looking at that part. So then you will see that this current is actually very small in comparison to the current from the collector. But for now, you can see that for a very small change in the voltage, I see a big change in the current. Current is increasing. And you saw this behavior in the forward bias characteristics of a PN junction diode, because now it is just a PN junction for us, right? Because we are ignoring the other part. So as I am increasing this voltage, 0.7, 0.8, 0.9, even very small change, I will see a big current flowing out of the base, because now I have overcome the potential barrier of this junction, and then this current will keep on increasing, and VCE is fixed at 10 volts. So for this experiment, first we will fix 10 volts between the collector and emitter. I will set the voltage across this power supply 10 volts, and then I will do this experiment. I will slowly change this voltage across base and emitter 0, 0.2, 0.3, 0.4, and after 0.6 of course I will see some current which is coming out of the base. And now you know what is that current. When electrons go into the basement, a small fraction of them will take part in the recombination. They will fill this hole, then they will jump to other hole. In this way we will see some current, and this is what the input characteristics are showing. Vc is fixed, and then I can see some current. This current is in microampere. So remember that unit, because next when we will see the output characteristics of this setup, you will see that this current is nothing when we will compare this with the current coming out of the collector, this IC, when we will measure in the output, because now we are only considering the input characteristics. So this current, and just remember the unit, because just don't see the number here like it is 180. See the unit is microampere, because the scale may be different for the output characteristics and numbers are small, but you have to see the unit, because if unit is micro and maybe the unit for output characteristics, they are different. So this is the input characteristics of the transistor in common emitter mode. So what does it mean? It means that now I can fix the I current from the base, because now I know that for voltage, maybe for 0.61 I get some current IB, and then if I go a little bit 0.65, 0.66, so I can see like I get 20 micro ampere current from the basement, and then I get 40 microampere at what voltage. So I know that what voltage should I set across the base and emitter so that I get a constant current. Because of course when I set a voltage, for example here whatever voltage it is, if I set a voltage, then the current from the base will be constant 20 microampere, and it will remain 20 ampere, it will never change, right? And then if I want more current, maybe 40, then I will set this voltage, corresponding voltage across maybe around zero point 0.8. If I set the voltage of zero point 0.8, then across the base and emitter, so current coming out of the base will be around 40 microampere. And if I leave the voltage here, I don't change it further, this is the constant current which is coming out of the base, and it will never change, right? Okay, because I want to compare the base current and the corresponding current from the collectors, because I want to make a comparison that for how much current, corresponding current from IB. For example, if I set the current from the basement at 40 or 20 microampere, I want to see for this 20 ampere what will be the collector current. And then next I will change this current, base current, to 40 microampere. Then I would want to see like what is the corresponding collector current, and similarly I can go on. So the purpose of this curve is that we want to know that for what voltage we can get the current, so that I will always set that voltage and I will always get that current. Then I can do rest of the experiment with the output. First I will fix the current. For example, the first value is 20 microampere. So if I set the voltage, the suitable voltage, so that current from the base is 20 microampere, then I will just leave this input setup, I will never change. Then I will come to the output setup. I will see like what can I do with the VCE and the collector current, and this is where we will see the output characteristics. And here is the output characteristic curves of common emitter transistor. You see, for example, first I fix the current from the base at 10 microampere. So now current is there. I adjusted a suitable voltage VBE from the input curve. So when I set this voltage across base and emitter, output current from the base will be here, and we just saw that this will be constant. Once I set a suitable voltage, the current from the base will be 10 microampere. So now it is fixed. Now I will come to the output part. I will come at the output part, and I will, because here I have the choice, I can change this voltage. Because if you see, this is a DC power supply, and I can just move the knob to increase this voltage. So I can just start from 0, and then I will measure the current IC. So because now that current is fixed, I will not change the input. VB is fixed, and the corresponding current which is coming from the base is 10 microampere. Now I will come to the output. So I will set the voltage at 0, and I will measure the corresponding IC current with any emitter in the circuit. If I just apply it, and I can just see like what is the current, and I just set it at 0. So this output characteristic curves tells me that at 0, of course, the output current will be 0. And then I will set that voltage here, the voltage CE, this to maybe 1 volts, 2 volts. So I will just change this voltage. 0 and then 1 and then 2 and 3. I will keep on increasing, and every time when I increase, for example 1, I will measure the corresponding collector current. Then I will change it to 2 volts. I will measure the corresponding current IC. So in this way I can make this graph. You see, so for each collector voltage I am changing it to 2 volts. I measure the corresponding collector current, which is here. Whatever value I get, I just draw this point. Then I set the voltage across the collector and emitter to 4 volts, and then I will just see the current, corresponding current. So you see, even if I am increasing the voltage, current is same. It's around 1.8, and let me check that what is the unit. It's milliamperes. So that's why I told you that when you want to compare the current from the base, or even we have the values here, it's 10 microampere, but here you are getting about, because I am not sure the resolution of the graph is too small, it should be around 1.8 or 7 maybe milliampere. This is in milliampere, remember that. For 10 microampere current from the base, you are getting 1.7 or 1.8 milliampere current. And this is a huge amplification. Believe me that 10 into 10 power negative 6 ampere. And then here you have a current of, just take the lower value, 1.7 milliampere. So let me give you a rough idea, like how much amplification is this. Because for a base current of 10 microampere, you have already fixed it. You are getting a current at the collector, no matter what is the voltage across the collector and emitter. You see, even if the voltage is changing, but that current is constant at the you are getting from the collector, whatever is the voltage. So you don't have to worry about that. So for 10 microampere current from the base, and if I want to show this number in the decimal places, you will get some idea. It is like this, ampere. And if I want to express this one in simple decimals, it should be 17 ampere. So this is the current. This is the current at the base you are getting right now, and this is the current the corresponding current at the collector you are getting. And now, do you have any idea that how much amplification you are getting? Now, if I want to have a comparison, if I multiply it with 170, I get an answer 0.0017 ampere. So you see, the amplification is 170 times of the current from the base. Mean the base current and the current at the collector current is 170 times the base current, and that's why I'm getting it is a huge amplification. And it doesn't matter whatever voltage you set across the collector and emitter, it is not changing. Whatever VCE is, you are getting a huge current for a small. So the next, when now suppose you want to change here the voltage, you change the voltage using this curve, you see, because now the next is for example 20 microampere, you want to get the current from the base 20 microamperes. If you want to get 20, you will set the voltage across zero point 0.7 or close to 7 across the base and emitter, and when you will set that voltage, the current you will get from the base should be 20, and you will just leave it there. So you just leave it there when you are getting the current from the base, and now you will see what is the current you are getting from IC. And in the meanwhile, you will also change this voltage as well, just to see like what happens to the current. And then once again you see that for 20 microampere you get a constant current from the collector, which is around 3 milliampere. Once again, it's a huge value. If you want me to give the idea, 20 microampere, so it's 20 into 10 power negative 6 ampere, and the this is your current from the base, and here is the current from the collector. So for 20 the current is about 3 milliampere, and it's 0.0002 ampere, and this 3 milliampere is 0.003. So if you multiply this IB with 150, you get 0.003 ampere. So you see, the amplification is now 150 times. You are getting amplification 150 times the base current. So in this way, if you keep on checking, like now set the current at the base using this curve, because now you want 30 microampere or 40 microampere, so you will see this input characteristic are 40 ampere. Then you will see the corresponding voltage you need to apply across the base and emitter. So then after setting that voltage, you will get the 40 microampere current, then just leave it in this state, and now see the current at the collector, and then you will also change this VCE across emitter and collector and see what happens. So you can see that for a small base current you get a huge amplification the for that current at the collector terminal. So you are using this transistor as an amplifier, and this amplification is really good. So do you know how did I calculate this amplification factor, for example 150 and 170 in that case? It is called beta factor, and the formula is current at the collector and then current you are getting from the base. This is called current gain because it tells us how much amplification you are getting. I mean, you had very little current at the base, but you are getting very huge current at the collector. So there is an amplification because the current from 20 microampere and then it scales up to 3 milliampere. So how much is the quantity? This is a quantitative way to get the current gain beta factor. It is the ratio of the collector current to the base current, and you will get this factor. For example, if you divide these two values, you will get 150 is the current gain. In the previous case it was 170, so you can calculate for all of these cases. And the last, that the region, this one, this region is the region where the both junctions are in forward biasing. That's why we call it saturation region. That this is the region where the transistor is in saturation mode or on mode. It means both junctions are in forward biasing, and even if the voltage across the collector or emitter or whatever, you will just see increase in the current because now they are behaving like a conductor. There is nothing special in that one. So we just label it this name as saturation region because transistor is operating in saturation mode when both the junctions are in forward bias mode. Similarly, this region is cutoff region. This is the region when both the junctions of the transistor are in reverse bias mode. So no matter what is the voltage across the VCE collector and emitter, or whatever voltage you apply across base and emitter, you will not see any current and it will be around zero. So this region is cutoff region when both junctions are in reverse bias mode.